Now we're going to talk about the strength of the correlation coefficient. So the top here, the sum of the products, tells you the variability accounted for by the association between both your variables. The bottom here is the expected variability for a perfect correlation. So if the variability accounted for by the association is equal to the expected variability for a perfect correlation, then R will be 1 or negative 1. This means all the variability is accounted for by the association. So if the sum of the products is equal to the square root of the sum of squares multiplied together, so the top is equal to the bottom, right? If we divide something by itself, then it's going to equal 1. And if it was a negative on the top and a positive on the bottom, but the two numbers are the same, then we're going to get a negative 1. So if the variability accounted for by the association, which is the top, is equal to the expected variability for the perfect correlation, which is the bottom, then R will be 1 or negative 1. So it means that the association accounts for all this variability. If there is no variability accounted for by the association, then the R will be 0. So if the sum of the products is 0, that means there's no variability accounted for by the association, then the whole correlation coefficient will be 0. And then if some of the variability is accounted for, then the R will be above 0 and below 1, or above negative 1 and below 0. So here is kind of a number line of strength. In the middle we have a correlation of 0. That means there's no correlation. And the further you go away from 0, the stronger the correlation. So you want to remember that strength is not about the sign. So a negative 0.5 and a 0.5 correlation have the same strength. A negative 1 correlation and a positive 1 have the same strength. And the closer it is to positive 1 or negative 1, the stronger it is, and the closer it is to 0, the weaker it is. So as you go away from 0, the stronger the correlation is. You just have to forget about the sign when you're talking about strength. The sign is only about the direction. Here's a perfect positive correlation. Here's our data. So stress goes up and so does depression. So each time stress goes up by 1 unit, depression goes up by 3 units. So we go from 3 to 6 because it goes from 1 to 2 because it's going up by 1 unit. And then we go from 2 to 3 for stress, so depression goes up by 3. But then we go from 3 to 5, so stress is going up 2 units, so that means depression has to go up by 6. But for each unit that stress goes up, depression goes up by 3 units. And that's consistent. It's consistent. So that means that R will equal 1. It's a perfect correlation and it's positive because they're going up for both variables. They're going the same direction. Here's a perfect negative correlation. So as stress goes up by 1 unit, happiness goes down by 1 unit. So they're moving in opposite directions. So this would be a perfect correlation because it's consistently moving the same rate, but this would be a negative 1 because as stress increases, happiness decreases, or you can say as stress decreases, happiness increases. Here's a strong strength. So stress is going up and depression is going up also, but it's not a consistent rate. So we go from 4 to 9, so that's 5 units, and then 9 to 12, that's 3 units, and then 12 to 15, that's 3 units. So about 4 units each time, but it's not the same amount each time, or for each unit that stress increases It's not going up at the same rate exactly, but it's pretty close. So this correlation is 0.99, and it's really close to 1. Here's a weak strength, so stress is going up, and then we go up, um, or we go down most of the time for happiness. So from 22 to 12, we're going down, but then we get to 12 to 20, we go up, and then from 20 to 15, we go down. So most of the time, happiness is going down as stress increases, but there is that one person that has um, a happiness level of 20, even though the stress is at 4. So that's a little bit unusual. So the strength is 0.24. So we have a negative correlation here because stress is going up and happiness is going down, and we have a negative 0.24, which is closer to 0. So this is a weak correlation. Here's no correlation. So as stress goes up, your number of freckles, there's no pattern to it. So we go from 15 to 0, that goes down, then goes 0 to 20, that goes up, and then 20 to 5, that goes down. So there's just kind of random. There's no really pattern to it. So your correlation coefficient will be 0. I'm going to talk about the line of best fit, and that helps us determine the strength of the correlation when you look at a scatter plot. So here's my scatter plot, and we have this line of best fit, and the line of best fit, or the regression line, is just a line that we put to kind of summarize the data. So we put it in a spot where we think best fits the data. And remember, for Pearson correlation, it's always a linear relationship. So it's going to be linear and it's not going to be curved. Okay? And the line of best fit tries to decrease the distance between the dot and the line as much as possible for all the dots. So it tries to have the distances between the dot and the line to be as small as possible, and it does this for all of the dots. Okay, so it tries to make that distance very small for each of them. So that line of best fit kind of helps you determine the strength. So here is our scatter plot. Here's our dots, and here's our line of best fit. And how close the dots are to the line determines the strength. So here's a perfect positive correlation. So here's our data, and we're going to have R equals 1, because remember, as stress increases by a certain amount, depression increases by that another amount, but it's consistent. Remember, strength is consistency. So in this example, we have perfect consistency. So the dots will go on the dotted line because the rate of change is the same throughout. So if the dots are on the line, that's a perfect correlation. Here's a perfect negative correlation. Here's our data, and as stress increases by a certain amount, happiness will decrease by the same amount consistently. So remember, it's about consistency, about strength. This is going to be an R equals -1. The Pearson correlation coefficient will be -1. And so the dots are perfectly on the line of best fit. They don't stray at all. So this would be a perfect negative correlation that has a Pearson correlation coefficient of -1. So here's more examples of strength that aren't perfect. So on the top left we have a 0.7. It's positive, so the dots are pretty close. It's not perfect, so they're a little bit far away from the line, but not too far. And then we have on the bottom, right under it, a negative 0.7. So as you can see, the dots are the same for it's spaced the same as the first one, but now we're going in the opposite direction. And then in the middle we have a strength of 0.3 for both, but the top is a positive and the bottom is a negative. And so the dots are a little bit further away than for the 0.7s. And then the last scatter plots here have correlation coefficients of 0, and when you try to fit a line of best fit, it just makes a line that goes from the left to the right. It's horizontal. So it tries to make the distance between the dots as small as possible, and that's the best it can do. It's just to make a line like that. So if the line looks like that, that means your correlation coefficient is 0. Here's some examples of correlation coefficients, and we're going to order these by strength. And we're going to go from weakest to strongest. The weakest will be 0. The next one will be 0.23. The next one will be negative 0.40. Then the next one will be 0.5. And then the next one will be negative 1. So it goes from the lowest number to the highest, ignoring the sign. So remember, strength is not about the sign, only the number. Here are the effect sizes suggested by Cohen. So Cohen says that if the coefficient, positive or negative, is between 0 and 0.3, so if you take the absolute value of the coefficient, and if it's between 0 and 0.3, Cohen considers this a weak correlation. If it's between 0.3 and 0.5, this is a moderate correlation. If it's between 0.5 and 1, that's a strong correlation. So these effect sizes are for complex psychological data. And so we kind of have low barriers for the coefficient. So for other sciences, they might have different standards. So for other sciences, you might have to have a 0.8 or something to have a strong correlation instead of just 0.5. That's kind of low. But the reason that the standards are kind of low is because correlations in psychology are really complex. So you're trying to see if your salary is correlated with your self-esteem, and it probably is, because the more you make, the more self-esteem you're going to have, but it's very complex, and those are a lot of things that's going to affect your self-esteem. So for example, your relationships at home, maybe your education level, maybe if you enjoy your job, things that are going on in your life. So it's going to kind of moot that correlation down between salary and self-esteem. So if you find a correlation at all, then it's kind of promising. So we kind of have lower standards in psychology just because people are very complex. And so Cohen suggested these effect sizes for psychology, but if you're doing other sciences, they might have different standards.
You also need to remember that the Pearson correlation tells you nothing about the rate of change, which is the slope of a line. So here you can see that these two have the same Pearson correlation. They both have a Pearson correlation of 1, but they look different. So the first one has a higher slope than the second one on the right. But they both have a perfect positive correlation. So the correlation tells you about the consistency of how they move together. Or in other words, you can predict y with 100% accuracy if you know what x is. Or the other way around, if you know what y is, you can predict x with 100% accuracy. And both of them, they both have consistent relationships. This perfect relationship. But in the first one on the left, as x increases, y increases by a larger amount than it does in the second one on the right hand side. So just remember that the Pearson correlation tells us nothing about the rate of change. The Pearson correlation actually is standardized, right? And we standardize it by dividing by the sum of squares for x and y, and that makes it from -1 to 1. And then we can see how strong that relationship is. So by standardizing it, we don't care about the slope now. If we cared about the slope, then we would calculate the slope. But in this instance, we just want to know how consistent or how accurate can we be when predicting y with x. And that's what the Pearson correlation tells us.
Also remember, it's only for linear relationships. So here we have the anxiety data and performance data. And remember, before in another video we had as anxiety increased, your performance increased. So you're getting anxious, so you study a lot, and so that increases your performance. But at a certain point, if you get too anxious, then you can't study because you're so anxious and worked up, and so then your performance starts to decrease. And so if you put that in a scatter plot, it looks like something like this. And so you can see as your stress increases, your anxiety, as your anxiety increases, your performance increases until a certain level, and then it starts to decrease. And if you try to put a linear line of best fit, then it'll look something like that, and that doesn't fit the data, right? And so a Pearson correlation coefficient for this data would be something around 0. Looks like it might be slightly positive, but it's going to be around 0, and it doesn't really represent the association of anxiety and performance. As you can see, it's a really, really strong correlation or association, but this linear line doesn't fit the data. You need a curved line. So remember that the Pearson correlation coefficient only works well for linear relationships and not curved relationships like this one. So here's the scatter plot again of anxiety and performance, and it's curved, right? And I'm going to put the average lines again. So here's the average for anxiety, and here's the average for performance. And so if you find the products for each quadrant, this quadrant will have negative products. This quadrant will have negative products as well. And then these quadrants, this one and this one, will have positive products. And so if you add all the products up, they'll just cancel each other out because there's about the same in each. And so for this one, we'll actually get a Pearson correlation coefficient of about 0. And that's saying that there's no real correlation, but as you can see, anxiety and performance are related to each other, but the Pearson correlation coefficient doesn't do a sufficient job in capturing that relationship. So only do the Pearson correlation coefficient for linear relationships. So don't do this.
So remember, correlation does not equal causation. So here we have two scatter plots, and on the first one we have variable A as the x-axis on the x-axis and variable B on the y-axis. We have a correlation of 0.7. And on the second scatter plot we have variable B on the x-axis and variable A on the y-axis. And we still have a correlation of 0.7, so it doesn't matter which way you really put it or do the math, you'll get the same correlation, right? The math doesn't distinguish between the x and the y variable, really. Now, when you graph it on a scatter plot, you will want to make a decision on which one to put on the x-axis and which one to put on the y-axis because it makes like theoretical sense. But the math doesn't know the difference. So if you say variable A causes B, you want to be like on the left axis, and if you say variable B causes variable A, you want to make it like on the right axis. But it could be either way, or it could even be a third variable cause, and one doesn't cause the other one, is actually a third variable causing both variable A and B to increase at the same time, and then they happen to be correlated and associated with each other, but they really don't have a relationship with each other. So for example, ice cream and murder rates. So those are correlated together, but ice cream doesn't cause murder and murder doesn't cause people to eat ice cream. So what is happening? Well, what's happening is when it's hot outside, people eat more ice cream, right? That makes sense. And people are out more, so they just happen to run into each other more and murder each other more for some reason. So that third variable, the temperature, is causing variable A and variable B to be correlated with each other even though they're not related in any meaningful way. So just keep that in mind, that correlation does not equal causation. So if you need more info about this, go back to your research methods phase and read about it.